This optional video will be more or less the last word that we have on sorting for the purposes of this course, and it'll answer the question, can we do better? Remember, that's the mantra of any good algorithm designer. I've shown you n log n algorithms for sorting, merge sort in the worst case, quick sort on average. Can we do better than n log n? Indeed, for the selection problem, we saw we could do better than n log n. We could do linear time. Maybe we can do linear time for sorting as well. The purpose of this video is to explain to you why we cannot do sorting in linear time. So this is a rare problem where we understand quite precisely how well it can be solved, at least for a particular class of algorithms called comparison-based sorts, which I'll explain in a moment. So here's the formal theorem I want to give you the gist of in this video. So in addition to restricting to comparison-based sorts, which is necessary, as we'll see in a second, I'm going to make a second assumption which is not necessary, but is convenient for the lecture, which is that I'm going to think only about deterministic algorithms for the moment. I encourage you to think about why the same style of argument gives an n log n lower bound on the expected running time of any randomized algorithm. Maybe I'll put that on the course side as an optional theory problem. So in particular, quicksort is optimal in the randomized sense. It has average n log n time, and again, the claim is that no comparison-based sort can be better than that, even on average. So I need to tell you what I mean by a comparison-based sorting algorithm. What it means, it's a sorting algorithm that accesses the elements of the input array only via comparisons. It does not do any kind of direct manipulation on a single array element. All it does is it picks pairs of elements and asks the question, is the left one bigger or is the right one bigger? I like to think of comparison-based sorts as general purpose sorting routines. They make no assumptions about what the data is other than that it's from some totally ordered set. I like to think of it really as a function that takes as an argument a function pointer that allows it to do comparisons between abstract data types. There's no way to access the guts of the elements. All you can do is go through this API which allows you to make comparisons. And indeed, if you look at the sorting routine in, say, the Unix operating system, that's exactly how it's set up. You just pass it a function pointer to a comparison operator. I know this sounds super abstract, so I think it becomes clear once we talk about some examples. There's famous examples of comparison-based sorts, including everything we've discussed in the class so far. There's also famous examples of non-comparison-based sorts, which we're not going to cover, but perhaps some of you have heard of, or at the very least, they're easy to look up on Wikipedia or wherever. So examples include the two sorting algorithms we've discussed so far, merge sort. The only way that merge sort interacts with the elements in the input array is by comparing them and by copying them. Similarly, the only thing quicksort does with the input array elements is compare them and swap them in place. For those of you that know about the heap data structure, which we'll be reviewing later in the class, heap sort, where you just heapify a bunch of elements and then extract the minimum n times, that also uses only comparisons. So what are some famous non-examples? I think this will make it even more clear what we're talking about. So bucket sort is one very useful one. So bucket sort is used most frequently when you have some kind of distributional assumption on the data that you're sorting. And remember, that's exactly what I'm focusing on avoiding in this class. I'm focusing on general purpose subroutines where you don't know anything about the data. If you do know stuff about the data, bucket sort can sometimes be a really useful method. For example, suppose you can model your data as IID samples from the uniform distribution on 0, 1. So they're all rational numbers, bigger than 0, less than 1, and you expect them to be evenly spread through that interval. Then what you can do in bucket sort is you can just pre-allocate n buckets where you're going to collect these elements. Each one is going to have the same width, 1 over n. The first bucket, you just do a linear pass through the input array. Everything that's between 0 and 1 over n, you stick in the first bucket. Everything between 1 over n and 2 over n, you stick in the second bucket. 2 over n and 3 over n, you stick in the third bucket, and so on. So with a single pass, you've classified the input elements according to which bucket they belong in. Now, because the data is assumed to be uniform at random, that means you expect each of the buckets to have a very small population, just a few elements in it. So remember, if elements are drawn uniform from the interval 0, 1, then it's equally likely to be in each of the n available buckets. And since there's n elements, that means you only expect 1 element per bucket. So each one is going to have a very small population. Having bucketed the data, you can now just use, say, insertion sort on each bucket independently. You're going to be doing insertion sort on a tiny number of elements, so that'll run in constant time, and then there's going to be a linear number of buckets, so it's linear time overall. So the upshot is, if you're willing to make really strong assumptions about your data, like it's drawn uniformly at random from the interval 0, 1, then there is not an n log n lower bound. In fact, you can elude the lower bound and sort in linear time. So just to be clear, in what sense is bucket sort not comparison-based? In what sense does it look at the guts of its elements and do something other than access them by pairs of comparisons? Well, it actually looks at an element in the input array and it says, what is its value? And it checks if its value is 0.17 versus 0.27 versus 0.77. And according to what value it sees inside this element, it makes the decision of which bucket to allocate it to. So it actually stares at the guts of an element to decide what to do next. Another non-example, which can be quite useful, is counting sort. So this sorting algorithm is good when your data, again, we're going to make an assumption on the data, when they're integers and they're small integers. So say they're between 0 and k, where k is, say, ideally at most linear in n. So then what you do is you do a single pass through the input array. Again, you just bucket the elements according to what their value is. It's somewhere between 0 and k, and it's an integer by assumption. So you need k buckets, and then you do a pass, and you sort of depopulate the buckets and copy them into an output array, and that gives you a sorting algorithm which runs in time O of n plus k, where k is the size of the biggest integer. So the upshot with counting sort is that if you're willing to assume the data are integers, bounded above by some factor linear in n, proportional to n, then you can sort them in linear time. Again, counting sort does not access the array elements merely through comparisons. It actually stares at an element, figures out what its value is, and uses that value to determine what bucket to put the element in. So in that sense, it's not a comparison-based sort, and it can, under various assumptions, beat the n log n lower bound. So a final example is the well-known algorithm called radix sort. I think of this as sort of an extension of counting sort, although you don't have to use counting sort as the inner loop. You can use other so-called stable sorts as well. This is stuff you can read about in many programming books or on the web. And the upshot of radix sort is you assume that the data are integers. You think of them in digit representation, say binary representation, and now you just sort one bit at a time, starting from the least significant bits and going all the way out to the most significant bits. And so the upshot of radix sort, it's an extension of counting sort in the sense that if your data is integers that are not too big, polynomially bounded in n, then it lets you sort in linear time. So summarizing, a comparison-based sort is one that can only access the input array through this API that lets you do comparisons between two elements. You cannot access the value of an element, so in particular, you cannot do any kind of bucketing technique. Bucket sort, counting sort, and radix sort all fundamentally are doing some kind of bucketing, and that's why when you're willing to make assumptions about what the data is and how you are permitted to access that data, that's why you can bypass, in all of those cases, this n log n lower bound. But if you're stuck with a comparison-based sort, if you want to have something general purpose, you're going to be doing n log n comparisons in the worst case. Let's see why. So we have to prove a lower bound for every single comparison-based sorting method, so fix one. And let's focus on a particular input length, call it n. Okay, so now let's simplify our lives. Now that we're focused on a comparison-based sorting method, one that doesn't look at the values of the array elements just in the relative order, we may as well think of the array as just containing the elements 1, 2, 3, all the way up to n in some jumbled order. Now, some other algorithm could make use of the fact that everything is small integers, but a comparison-based sorting method cannot. So there's no loss in just thinking about an unsorted array containing the integers 1 to n inclusive. Now, despite seemingly restricting the space of inputs that we're thinking about, even here, there's kind of a lot of different inputs we got to worry about, right? So n elements can show up in n factorial different orderings, right? There's n choices for who the first element is, then n minus 1 choices for the second element, n minus 2 choices for the third element, and so on. So there's n factorial choices for how these elements are arranged in the input array. So I don't want to prove this super formally, but I want to give you the gist, I think the good intuition. Now we're interested in lower bounding the number of comparisons that this method makes in the worst case. So let's introduce a parameter k, which is its worst case number of comparisons. That is, for every input, each of these n factorial inputs, by assumption, this method makes no more than k comparisons. The idea behind the proof is that because we have n factorial fundamentally different inputs, the sorting method has to execute in a fundamentally different way on each of those inputs. But since the only thing that causes a branch in the execution of the sorting method is the resolution of a comparison, and we have only k comparisons, it can only have 2 to the k different execution paths. So that forces 2 to the k to be at least n factorial, and a calculation then shows that that forces k to be at least omega n log n. So let me just quickly fill in the details. So across all n factorial possible inputs, just as a thought experiment, we can imagine running this method n factorial times and just looking at the pattern of how do the comparisons resolve. Right? For each of these n factorial inputs, we run it through the sorting method. It makes comparison number 1, then comparison number 2, then comparison number 3, then comparison number 4, then comparison number 5. And it gets back a 0, then a 1, then a 1, then a 0. Maybe on some other input, it gets back a 1, then a 1, then a 0, then a 0, and so on. The point is, for each of these n factorial inputs, it makes at most k comparisons. We can associate that with a k-bit string. And because there's only k bits, we're only going to see 2 to the k different k-bit strings, 2 to the k different ways that a sequence of comparisons resolves. Now to finish the proof, we are going to apply something which I don't get to use as much as I'd like in an algorithms class, but it's always fun when it comes up, which is the pigeonhole principle. The pigeonhole principle, you'll recall, is the essentially obvious fact that if you try to stuff k plus 1 pigeons into just k cubbyholes, one of those cubbyholes has got to get 2 of the pigeons. Okay? At least one of the cubbyholes gets at least 2 pigeons. So for us, what are the pigeons and what are the holes? So our pigeons are these n factorial different inputs, the different ways you can scramble the integers 1 through n. What are our holes? Those are the 2 to the k different executions that this sorting method can possibly take on. Now, if the number of comparisons k used is so small that 2 to the k, the number of distinct executions, the number of distinct ways comparisons can resolve themselves, is less than the number of different inputs that have to get correctly sorted, then by the pigeonhole principle, one cubby gets 2 holes. That is, 2 different inputs get treated in exactly the same way by the sorting method. They are asked exactly the same k comparisons, and the comparisons resolve identically. Okay, so it's one jumbling of 1 through n, and you get a 0, 1, 1, 0, 1, and it's a totally different jumbling of n, and again you get a 0, 1, 1, 0, 1. And if this happens, the algorithm is toast, in the sense that it's definitely not correct, right? Because we fed it 2 different inputs, and it is unable to resolve which of the 2 it is, right? So it may be one permutation of 1 through n, or this totally different permutation of 1 through n. The algorithm has tried to learn about what the input is through these k comparisons, but it has exactly the same data about the input in the 2 cases. So if it outputs the correct sorted version in one case, it's going to get the other one wrong. So you can't have a common execution of a sorting algorithm unscramble totally different permutations. It cannot be done. So what have we learned? We've learned that by correctness, 2 to the k is in fact at least n factorial. So how does that help us? Well, we want to lower bound k. K is the number of comparisons this arbitrary sorting method is using. We want to show that's at least n log n. So to lower bound k, we better lower bound n factorial. So, you could use Stirling's approximation or something fancy, but we don't need anything fancy here. We'll just do something super crude. We'll just say, well, look, this is the product of n things, right? N times n minus 1 times n minus 2, blah, 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 blah. And the largest of those, the n over 2 largest of those n terms are all at least n over 2. The rest we'll just ignore. Pretty sloppy, but it gives us a lower bound of n divided by 2 raised to the n divided by 2. Now we'll just take log base 2 of both sides, and we get that k is at least n over 2 log base 2 of n over 2, also known as omega of n log n. And that, my friends, is why a correct deterministic sorting algorithm that's comparison based has got to use n log n comparisons in the worst case.